My name is Tiago, and today I will present you our paper titled HLS to FPGAs, Extending Software Regions via Transformations and Offloading Functions to the CPU. Let's start off with a little bit of background. I think we are all familiar with the concept of accelerating a C or C++ application using an FPGA. In essence, we try to find code regions that could benefit from FPGA acceleration, and we synthesize the hardware design by using high-level synthesis tools or HLS. When we try to apply this process to large C and C++ applications, we usually need to map the application onto a task model and try to find a cluster of tasks that can all be offloaded together to the FPGA. The problem is that when we use large applications instead of the typical simple kernels that are more commonly used in HLS, we run into HLS restrictions that prevent tasks from being synthesized. Some of these are pointer restrictions, like double dereferencing, the lack of support for dynamic memory allocations, no recursion, no system calls, and so on. Therefore, if we want to create large clusters for offloading and go beyond simple kernels, we need to find a way to overcome these limitations. I think this is better illustrated with an example. For instance, in this application here, we may want to offload all of these tasks, as they might constitute a hotspot in the program. However, there are two non-synthesizable tasks, with a memory allocation in calloc and a system call in printf. This only allows us to offload the innermost loop, as well as the previous task, requiring us to split the computation into two kernels. If we didn't have these limitations, we would have a single kernel that wouldn't incur in any unnecessary communications overhead, and it would allow us to explore inter-loop optimizations that wouldn't be possible otherwise. Now let's look at our methodology for solving this issue, which consists in providing a set of automated source-to-source transformations that fix some of these HLS limitations. Let's start by looking at structs, which are really at the core of many of these issues. For instance, this struct over here represents an image, and it contains a pointer to the image's data. This causes two problems in synthesis. First, if you have a pointer to a struct, you would end up with a pointer to a pointer, which isn't synthesizable. And second, many of these structs are allocated dynamically, which is also not allowed. This struct in specific is from the Cortex Suite benchmark suite, and it is used by every application in the suite, which severely limits the size of the clusters that we can generate for accelerating those applications. So, what's the solution? We can solve these limitations by using two transformations. Let's say we have a source code like this with a dynamically allocated struct pointer. We start by applying struct flattening over the struct pointer, that is, turning its fields into separate variables and updating our references and initializations accordingly. In this case, the width and height fields were mapped to integer variables, and the data field was mapped to a pointer initialized by a dynamic memory allocation. Then we have two options to get rid of that memory allocation. We can hoist it up the call chain to the function that calls through and just communicate the pointer through an argument, or we can convert the dynamic memory allocation into a static array, provided of course that we know the size at compile time. Now, let's see how we deal with system calls. If you have code with heavy computations interleaved with a system call, for instance printf, you would have an execution model like this on a CPU. So you would do the computations, then you would do the printf, then more computations, and so on and so forth. If we map this to an FPGA as is, we would need to split the computations into separate kernels and keep returning to the CPU host every time we want to do a print. Once again, we'd be incurring in additional communication overheads, and it is a less than optimal way of having this entire region on the FPGA. Our solution for this issue focuses on a subset of system calls, in particular those whose return value either isn't commonly acknowledged by the program, such as printf, or those that don't have a return value at all. On the FPGA side, we trigger these calls asynchronously through a fire and forget mechanism, where the kernel places the argument on a buffer and just keeps executing. The host, on the other hand, will be constantly polling those buffers, looking for call arguments, and it will execute the system call as soon as it finds those arguments. It's an asynchronous mechanism in that it eventually executes the calls rather than immediately executing them, but it still preserves all program semantics. Let's quickly look at an example of all of this put together. If we look at this region, only fizz is synthesizable because of the calls to calloc, printf, and free in the region. We can start by hoisting the calls to calloc and free by moving them up to the callee. Then we convert the call to printf to an asynchronous call to the host, which makes the bar task completely synthesizable. And as both foo and bar are synthesizable, we can wrap them together into a single cluster and use that for offloading. This is a very simple example, but it is easy to see how this could scale with dozens or even hundreds of tasks, which should be more representative of a real-world application. Finally, we demonstrate the usefulness of these transformations using some case studies. Our case studies use 4 applications: disparity and texture synthesis from Cortex Suite, spam filter from Rosetta, and finally the inference part of Llama 2, a large language model. In terms of metrics, we are looking at the size of the clusters that we can generate and their impact on the HLS design. And finally, as I have said before, our transformations are fully automatized. We achieve this by extending the Guava C and C++ source-to-source compiler, which we also use to generate the task graphs for the applications. We are also targeting the embedded CPU and FPGA space using Vitis, and in particular using the ZCU102 board as our hardware target. Our first case study is measuring the impact of hoisting and struct flattening on Cortex Suite. So, if we look at the disparity benchmark, we can see that without applying any transformation, we can only find 2 small clusters for offloading, one with 5 tasks and another with a single task, corresponding to 42 and 8% of the total tasks in the program, respectively. By applying the transformations though, we can bring that number up to 92%, as we can now have the entire program on a single cluster except for a few mallocs. We still have the headroom to improve that, as we can map some of them, and in this specific case the redsath malloc, into a static array, which leads to slightly better latency at the cost of more block RAMs. Our second use case is using the asynchronous call mechanism to portray a software-centric debugging workflow using that asynchronous call mechanism. The spam filter application from Rosetta is already completely synthesizable and doesn't require any transformations. However, if we want to debug the application using a software-centric flow, like for instance inserting printfs or asserts, we couldn't really do that on the FPGA. Except, of course, if we use the asynchronous call mechanism, we can automatically generate all the asynchronous calls for the application and debug the hardware design using the exact same approach that is used by software developers. We also use this to show the impact of the asynchronous call mechanism on the HLS design, which in this case comes at an extra second of latency with minimal resource overhead. Finally, we look at Llama 2. This application predicts tokens for a given prompt and writes a token using printf every time it predicts that token. It's kind of like that scrolling effect of one word at a time that you often see when you use LLMs. So, as is, the application keeps going back and forth between the FPGA, which does a prediction, and the CPU, which prints the result. This is very inefficient, as we would be incurring in communication costs every time we call the FPGA, and it would be very useful to have the FPGA predict all tokens in one go, while also printing them as they become ready. Once again, if we use the asynchronous call mechanism, we can fit every single task on the FPGA, while also retaining the program semantics when it comes to printing tokens as soon as they are generated. To conclude, we have proposed a set of source-to-source code transformations that enable the synthesizability of previously non-synthesizable tasks, allowing us to create increasingly larger regions for offloading, or at least having more options to pursue when deciding on a given partitioning for an application. In terms of future work, we want to apply these transformations to all Cortex Suite applications and explore their interplay when it comes to the size of the regions that we can create, and also we want to develop novel methods of hardware and software partitioning. Thank you for listening, and if you are watching live, I eagerly await your questions.